Hey guys, I'm back with a new video. In the previous video, we learned about the simple linear regression model in great depth. So in this video, let us learn about some performance evaluation metrics in case of simple linear regression. So let me select the pen, performance evaluation metrics. And then we will move forward to multiple linear regression and gradient descent in the next video. So performance evaluation and its metrics. So once you have developed a model, then comes the step of verifying the performance of the model by evaluating its statistical power of prediction. Now here we are concerned about computing the accuracy of our machine learning model when we are dealing with the performance evaluation of our machine learning model. By accuracy, we compute which machine learning model is best at identifying relationships and patterns. So we work on accuracy in this case. And we compute which machine learning model is best at identifying the relationships and patterns between variables in a dataset based on the input or training data. Now this was all in layman terms. Let us go to the actual metrics that are important for evaluation of the performance of your machine learning model. Though we will not be discussing all of the metrics, we will discuss some of the most prominent metrics in this video, which are RSE, which is known as your residual square error, and then we have something called as Rsquare, which is the coefficient of determination. So coefficient of determination. In the previous videos, we had discussed about the regression equation for simple linear regression, which is of the form y is equals to m0 plus m1x plus some error element. So I can say error. No matter how performant your machine learning model is, there is always an error element that is associated to your machine learning model, which you cannot get rid of completely. This error element makes it impossible for us to succeed in our quest to the best optimal 100% performant model. Though you can get close to 100%, but in practical you can never achieve an accuracy of 100%. There will always be an error element in your model, even though negligible, but it will always be there. And here comes the concept of RSE, which tells us how much will our predicted value deviates from the actual value on an average. So let me write this down. So I will clear up the screen. So RSE, the residual square error, it tells us how much your predicted value deviates, how much your predicted value deviates from the actual value on an average. So do take a note of these definitions because they are very important for understanding the concepts that we will be learning later. Okay, so let me explain this using a scatter plot as we learn about the concept of residuals in our previous videos. Now, so let me trace this a bit better. Now here you can see that we had a predicted value y cap corresponding to a certain value of x. Okay, so we have seen this in the previous video. And say this, so I'm considering some point density here. Say for certain value of x, say x1, the value that was described in the data set for this particular value of input variable, say that be y1, and the predicted value by our model is this one which is lying on the line, so this will be y1 cap. Okay, and this difference was that we had discussed, that the residual sum of square errors that we had discussed in the previous video. So here you can see we have a predicted value y1 cap corresponding to a certain value of x1, which is p1 that we got using our model. And then let us say, so I can term this as p1 also. So this is a predicted value that we got using our model, and then let us say that we have the real value of y that was represented by the training data for the same value of x, that is x1. So this is your actual value. Okay, so you are getting that from dataset. Then you can see that the difference between the predicted value, which is y cap, and the real value, which is y1, is this real thing. Okay, this difference between y1 cap and y1 is your error. Okay, it is your residual thing, so you can say it is your residual. This we have already seen in the previous video. In RSE, what you can do is you can trace two other lines. So let me show you this with a separate diagram. So we have the same line, and let this be y1 cap corresponding to x1 input variable, and let this be your y1, your real value that you're getting from the dataset. Okay, this is your residual, the difference between these points. Now you can now draw or trace two other lines other than the regression line that we are already having, one at the top of our regression line, which I will represent using a red shade like this, and the other one at the bottom of it. So I will use say green shade for this. Okay, as you can see in the scatter plot that I have drawn. Now what these lines actually depict is they tell us the average amount of variance or the deviation in terms of your predicted values and the real values. So this margin is basically telling you the average amount of variance or deviation in terms of your predicted values and the real values. The margin that you are seeing here is known as RSE. So this is your RSE, this thing. Okay, this is your RSE, the residual square error. So the margin that you can see here is known as RSE. To compute the value of RSE, we can write residual, first I will write residual sum of squares that we have discussed in the previous video. So RSS will be R1 square, okay, plus R2 square. We have seen this in the previous video. R3 square, R4 square, R5 square, say to Rn square, and we can write this as y1 minus y1 cap. So y1 is your real value, y1 cap is your predicted value, then y2 minus y2 cap whole square, and so on. We know that the y is your real value and the cap, any cap on your y value, is the predicted value. Okay, now to compute the RSE from the RSS value, you simply have to take the square root So RSE will be, you take the square root, okay, of the product of 1 by n minus 2 into RSS, okay, where n is your number of rows in your data set. Now one more thing that you need to understand is that the larger the margin, okay, this margin which is your RSE, or you can say this total margin, if this margin is larger than the value of RSE, poorer will be the performance of your model, okay. To sum it up, larger the margin, the more uncertain we are about our predictions, so we need to minimize this uncertainty, which is the margin of course, and thus improve the performance of a model, which is our end goal. Now what I will do is, let us consider two other datasets to understand this in more detail. So let us say we have two scatter plots, and let us assume that the equation of our regression line is same in case of both the datasets, okay. So we have the same line in case of both the datasets, but there is a difference between the two datasets. The one thing that you can see is that in the very first dataset that I'm going to consider, the point density for a scatter plot is going to be more variable, okay. So it's variable. So this is our dataset D1, and for the case of dataset D2, the point density be more dense, like this. Let me represent this using more points to represent a dense point density, okay. Now if we take into consideration RSE here, we can see that if I draw two lines here again, okay, and say this one, and same for our second data set D2, and the second line, which is of course a red in shade, okay. So if we take into consideration RSE here, we can see that the two lines for our regression lines look somewhat like this, okay, and it can be seen clearly that the RSE for a dataset D2, so this is your RSE for dataset D2, and you can clearly see that, you can clearly observe that it is a lot lower than RSE for dataset D1. As you can see here that RSE for dataset 1 is a lot larger than RSE for dataset 2. So RSE for dataset D1 is a lot larger than RSE for dataset D2. And what does this mean? This simply means that there is a lot of margin that needs to be covered by the model in case of dataset D1, and because of this very large margin, there is an increasing affinity of your machine learning model to make mistakes in the predictions. Now contrary to the case of dataset D1, there is not much margin for the model to cover in case of dataset D2, okay. The margin is already very less compared to the margin that you are having in dataset D1. Now let us discuss about the performance evaluation from perspective of another metric, which is known as Rsquare, okay, also known as coefficient of determination. Let me explain this metric by again making use of the same scatter plots. So consider the same two scatter plots again. And here we are having variable point density, and for say dataset D2, let us have a dense point density. So the points are more dense in case of dataset D2, and they are more variable in case of dataset D1. Okay, now there is one issue with RSE, that you cannot tell what is good value of RSE for a model, because it depends upon the distribution of the point density in your dataset, and also on the nature of the domain of the problem that you're working on. The problem here is that using the value of RSE, You cannot tell under what scenario your model is a good model and under what scenario it is not one. Now, to counteract the effect of the problem, we will learn about another metric which is known as R-square. So R-square is a measure of, so let me write this down. R-square, it is a measure, it's a measure of proportion of variability in Y as explained by X. So it is one of the most important performance metrics for evaluating the performance of your regression model. R-square can be defined in terms of mathematical equation like variance explained by the model upon total variance. So in our model, we can cover the entire variance. Then you can say that the value of R-square is 1 if you can cover entire variance when the variance explained by model is same as total variance, and if it cannot explain any amount of variance, then the value of R-square will be 0. Okay, so something like this, but it will never reach 1. So you can say 0 less than R-square less than 1. So R-square can also be expressed as TSS minus RSS upon TSS, or you can say 1 minus RSS upon TSS. Now TSS is summation from k1 to n yk minus y bar. So yk is a certain value of y, say for your kth row, and y bar is your mean value for your output variable. And then RSS, we know already that it is summation from k1 to n yk minus y cap. Okay, so as you can see in TSS, we are finding the difference between the actual value, which is your yk of our output variable, and the mean of the output variable, and in RSS we are finding the difference between the actual value and the predicted value of the output variable, which we have already discussed before. Now if I assume RSS to be 0, this term to be 0, which of course practically is not possible because there will always be some error element no matter what, then under this assumption we can write RSS as, if I put this term as 0, then under this assumption RSS R-square will come out to be TSS minus 0 upon TSS. Okay, and if TSS and TSS will get cancelled, and you will get RSS, not RSS, R-square as 1 under this assumption. Okay, so this is the case for the best model, which is not possible in reality. So in the next video we will work on the dataset that we had discussed before, and we will create a simple linear regression model for our dataset in the next video, after which we will start with multiple linear regression. So if you like the video, do give it a thumbs up, and I will see you guys in the very next video.